In this video, we'll be talking about how to solve logarithmic equations as well as how to solve exponential equations using logarithms. So first, let's start with solving logarithmic equations. So a logarithmic equation means I've got an equation, there's a log in it, and the x is somewhere inside the log. And we have got to figure out what is x equal to. So let's look at this example first. So say I want to solve log base 2 of x plus log base 2 of 3 is equal to 4. Your first step is to condense your log into a singular log if that's necessary. This means you're going to be using the power rule, the product rule, and the quotient rule to condense the log. So here I condense it to log base 2 of 3x is equal to 4. Then you're going to convert it to exponential form. So that's 2 to the 4th power is equal to 3x. And at this point, we're just going to solve for x. So 2 to the 4th power is 16. 16 equals 3x. Divide both sides of the equation by 3, and you're left with x is equal to 16 over 3. Now, one thing to be cautious of is something called extraneous solutions. Extraneous solutions are solutions that seem correct, but they make the argument or the inside of the log negative. Remember, you cannot plug any negative numbers into a logarithm. So what we need to do whenever we're solving a logarithm is at the end, make sure that none of our answers are extraneous solutions. And you do that by checking your answer, by plugging it back into the log. So let's take a look at this example right here. If I have log base 6 of x plus log base 6 of x minus 1 is equal to 1, I'm going to start by condensing that logarithm into one log using the product rule. Then I'm going to simplify, so I have log base 6 of x squared minus x is equal to 1. Then I'm going to rewrite it as an exponential, so 6 to the 1st power equals x squared minus x. Now what I have is a quadratic function. So I'm going to set the quadratic equal to 0, and then I'm going to factor it. So from this step, x squared minus x minus 6, I'm turning it into x minus 3 and x plus 2. And the reason I chose the minus 3 and the plus 2 is because negative 3 times 2 is negative 6, and negative 3 plus 2 is negative 1. And then your final step is just to figure out which x values are going to make each parenthesis equal to 0. So x equals 3 and x equals negative 2. So I found two answers here. So once you've found those two answers, you have to check them to see if they're extraneous solutions. So on this left side, I'm plugging in x equals 3. And I'm just going to plug it into my original equation. So log base 6 of 3 plus log base 6 of 3 minus 1. I'm just changing all the x's into 3's basically. And essentially what I'm checking for is to make sure that you don't get any negative numbers inside the log. So in this case, there's no negative numbers, so we're good to go. X equals 3 is a solution. Now jump to the right side where I start checking if x equals negative 2 is a solution. I have log base 6 of negative 2 plus log base 6 of negative 2 minus 1. Then I'm going to simplify the second set of parentheses to negative 3. Oh, this should be a parenthesis right here. Notice that we have negative numbers inside both of our logs at this point. That means that x equals negative 2 is not a valid solution. It would be an extraneous solution. Okay, so when I'm saying what my answers are, I would just write x equals negative 3. And you're always going to want to show your work to show that you checked to make sure that your solutions were not extraneous solutions. Okay, let's go ahead and do some examples of these. So, in example A, I don't need to worry about condensing the logarithm because it's already condensed as far as it can go. We just have one logarithm. So I'm going to rewrite this as an exponential equation. So 5 to the 1st power is equal to 3x minus 7. Now 5 to the 1st power is just 5. So 5 equals 3x minus 7. Then add 7 to both sides. So 12 is equal to 3x. Divide by 3. And 4 is equal to x. So that is my solution. Now what we want to do is check for extraneous solutions, always. So I'm just going to do that in my black pen over here. I'm just going to take that 4, and I'm going to plug it into my equation. So let me just erase this mess. So I'm going to have log base 5 of 3 times 4 minus 7 is equal to 1. Then I'm just going to simplify. So 3 times 4 is 12. 12 minus 7. Inside the logs, I have log base 5 of 5 is equal to 1. Since this 5 is positive, since I didn't get any negatives inside the log, it means that 4 is not an extraneous solution. This is also a good way to check your work. So in this case, I know that log base 5 of 5 is equal to 1. That's one of my log properties. So in addition to checking for extraneous solutions, you're also checking to make sure that you didn't make a mistake when you were solving. All right, let's go ahead and jump to the next problem, example B. So here I have 2 logs, so my first step is to condense them into one log. So log base 2 of 5x is equal to 3. Then I'm going to convert this into an exponential. So 2 to the third power is equal to 5x. 2 to the third power is 8, so I have 8 equals 5x. Divide both sides by 5. And 8 over 5 is equal to x. Okay. So that is a solution. I just need to double check and make sure it's not an extraneous solution. So I'm going to go back to my original problem. And wherever I see an x, I'm going to plug in 8 over 5. Okay. Now at this point, it looks pretty messy here, but I can already tell you right now that I know that this is not an extraneous solution because all of the arguments to my log are positive. So I can stop right here and say x equals 8 over 5. That is a valid solution. Now it's not a bad idea to think about continuing to evaluate these logs, condense them, and simplify them, just to make sure that 8/5 is a correct answer. So we know it's not an extraneous solution, but if you want to make sure that you didn't make a mistake earlier on, it might be a good idea to actually finish evaluating that. All right, let's take a look at this next example. So I have 2 logs here, so I'm going to start by condensing them. So log base 4, since I'm subtracting here, I'm going to do 3x minus 8 over 16 is equal to negative 2. Then I'm going to rewrite this as an exponential. So 4 to the negative 2 is equal to 3x minus 8 over 16. 4 to the negative 2 is 1/16. Remember, our negative exponents create fractions. So I'm left with 1 over 16 equals 3x minus 8 over 16. So here's something nice. If I have fractions on both sides and they're the same denominator, they can just cancel each other out. So I'm just left with 1 is equal to 3x minus 8. And that is a pretty simple equation to solve. Add 8 to both sides, divide by 3, and we get 3 is equal to x. So let's go ahead and check to confirm that this is not an extraneous solution. So I'm going to go back to my original problem, log base 4 of 3 times my x value, so 3 times 3 minus 8 minus log base 4 of 16 is equal to negative 2. Do a little bit of simplifying. 3 times 3 is 9. 9 minus 8 is 1. Try to write this a little bit smaller since I'm running into the next problem. Once I have my logs simplified and I notice that all the arguments are positive, I know that my solution is not extraneous. So here I can just put that there's no extraneous solutions. I'm just going to go ahead and make a box out of this that we know was part of the previous problem. Okay. So let's go ahead and do this next problem and see what this looks like. So I am first going to start by condensing my logs. So I have log base 4 of x times x minus 6 is equal to 2. Then I'm going to convert to an exponential. So 4 to the second power is equal to x times x minus 6. At this point, I'm going to want to do a little bit of simplifying here. So 4 squared is going to be 16. And then on the right side of my equation, I need to distribute this x inside. So it'd be x squared minus 6x. Then I have a quadratic. I know I have a quadratic because I have an x to the second power. So I'm going to set my equation equal to 0 by subtracting 16 from both sides. Now, the easiest way to solve a quadratic is to factor it. So when I'm factoring, I'm looking to separate this into two sets of parentheses. And I want to find two numbers that multiply to negative 16 and add up to negative 6. In this case, two numbers that work are negative 8 and positive 2. So if those are my factored forms, then my solutions are x equals 8 and x equals negative 2. So remember, they're always the opposite signs of what's in your parentheses. So these are my two supposed answers. I need to check to see if these are extraneous. So since I got two answers, I need to check both of them. So let's start by checking x equals 8. Okay. I'm just going to plug this into the right side of the left side of the equation, just for sake of space. So log base 4 of 8 plus log base 4 of 2. Well, both of those are positive logarithms. So 8 is a solution to my problem. So let's check x equals negative 2. Log base 4 of negative 2 plus log base 4 of negative 2 minus 6. Okay, I do not even need to go any further because I see right here I have a negative number inside my log. So that means that this is an extraneous solution. So under extraneous solutions, I'm going to put x equals negative 2. And I'm actually just going to cross it off from my solution box. Because even though x equals negative 2 seemed like a correct answer, it was actually an extraneous solution. Okay, what I'm going to do now is I'm going to have you press pause on this video. Try E and F. Okay, I will work through them as well, so go ahead and try these, and then when you come back and hit play, you'll be able to see all my work and the solutions to this. Alright, so here's the work and the solutions for these last two examples. In example E, we had one extraneous solution and one real solution. So the solution was x equals 7. And then in example F, we had two solutions and neither one was extraneous. So we just have two solutions to that logarithm. So one of the reasons that I really wanted to do example F and have you guys see that is that oftentimes students will find two solutions and they will assume that one of them has to be extraneous. And they'll often assume that the negative solution has to be extraneous. And that's sometimes the case, but not necessarily. So there are times when you're going to have multiple correct, real, non-extraneous solutions to a logarithmic equation. Okay. So we're going to go through one other type of equation, and this is solving an exponential equation. And the reason this is part of this video and this lesson is because we're going to solve this exponential equation using logarithms. So let's say I want to solve 3 times 2 to the x plus 1 is equal to 9. So the first thing we want to do is rewrite this in standard exponential form. And what that means is that you want to get just the number with the exponent all by itself on one side of the equation. So the way I did that here is I divided both sides by 3 to get rid of the 3 that was being multiplied in front. And that gave me 2 to the x plus 1 is equal to 3. Now we learned previously another way to solve exponential equations like this that involved changing the base on both sides of the equation to the same thing. The reason that we're doing it differently here is that we cannot write the right side of this equation as an exponent with a base of 2. So when that is the case, we have to use logarithms. So we are going to convert this from exponential form to logarithmic form. So log base 2 of 3 is equal to x plus 1. Then we need to get the x by itself. So I'm going to subtract 1 from both sides and have log base 2 of 3 minus 1 is equal to x. This might not look like a final answer, but it is. You're done. You could technically type this into a calculator and get a decimal, but if you have decimal, you're going to have to round. So by leaving it just like this with the logarithm in it, you've given me an exact answer, and that's what I want. One thing to be cautious of is that you cannot subtract this 3 and this 1. Okay? Lots of times people want to say, okay, well, that would then turn into log base 2 of 2 is equal to x. That is wrong. Okay? You can only subtract things within logarithms if they're actually both part of a log. But that 1 is not part of a log. So let's go ahead and work through a couple examples. So we're going to solve the following equations, and we're going to give exact values as answers, which means we're not going to see any decimals. So first I have 4 to the x is equal to 37. So first thing I want to do is make sure it's in standard exponential form, which it is in this case, because the 4 and its exponent are already by itself on the left side of the equation. Next I'm going to convert to logarithmic form. So log base 4 of 37 is equal to x. And then my final steps would be to get the x by itself, but that x is already by itself. So I'm done. X is equal to log base 4 of 37. And again, that might not feel like an answer because you've still got a log there, but that is an answer. Remember, you can type that into a calculator and you would get a solution there. All right, let's look at the next one. So b, you'll notice, is also already in standard exponential form. So I'm just going to convert it to logarithmic form. So log base 3 of 4.5 is equal to negative x. Last thing I want to do is get rid of that negative in front of the x. So I'm just going to divide both sides by a negative 1, which makes this the negative log base 3 of 4.5 is equal to x. And I'm done. We do not have to check for extraneous solutions here, but it's never a bad idea to plug your solution back into the equation to see if you got the right answer. Okay, let's do it again. C, we have 30 e to the 4x is equal to 600. So the first thing I want to do is I need to get this e to the 4x by itself on that side of the equation. So I basically need to get that 30 away. And I'm going to do that by dividing both sides of the equation by 30. So then I have e to the 4x is equal to 600 divided by 30, which is 20. And then I'm going to switch this to log form. So I have log base e of 20 is equal to 4x. Now before I try to get the x by itself, I'm going to rewrite this. Log base e, we have a special way of writing that. It's the natural log, so the ln. So I'm going to change that left side of the equation to the ln of 20 is equal to 4x. Then I'm going to go ahead and divide both sides by 4, get that x by itself. Now remember, you cannot divide that 20 by 4 because the 20 is inside the logarithm and the 4 is not inside the logarithm. So it's just going to look like a big fraction just like that. I'm going to let you guys work through D on your own. I'll put up the answer to that in 1 second. Let's go ahead and look at E together. So with E, I'm trying to get the 2 to the 4 minus x by itself. So I'm going to start by adding 7 to both sides. So I have 2 to the 4 minus x is equal to 21. Then I'm going to rewrite that as a log. So log base 2 of 21 is equal to 4 minus x. Then I just need to work on getting that x by itself. So I'm going to subtract 4 from both sides. Actually, you know what? Let's do it a different way. I'm going to add x to both sides. The reason why is because then my x becomes positive, and I always like having a positive x. And then I need to get rid of this log base 2 of 21. So I'm going to subtract log base 2 of 21 from both sides of the equation. Now I'll get x is equal to 4 minus the log base 2 of 21. Once the x is alone, you know you're finished. Okay, I'm going to let you guys try the last 2 examples, D and F, on your own. So hit pause on the video and then come back and double check your answers. Okay, hopefully you were able to find the right answers to D and F. Here they are. Problems like F. This is a long problem. It has a lot of steps to it, both before you convert to a logarithm and after. So just be really, really careful in all of your steps, and make sure that you are really being careful with your negatives and adding and subtracting negatives and positives. So hopefully this has helped you learn how to solve logarithmic equations as well as exponential equations.